Welcome back. So we are starting a new module that I refer to it as contextually constrained deep learning, where the idea is that in addition to, let's say, maximizing some notion of performance, for instance, finding a model that achieves a very low training error, finding a model that achieves a very good generalization, we also want to make sure that some other criteria are also satisfied. Okay? Obviously, this is a very broad topic. But we're going to focus on a couple of contexts that I feel are of our high importance, especially when it comes to the sort of the implications of deep learning to the society. So one of these contexts is basically the notion of privacy. So we're going to talk about privacy preserving deep learning. So let's recall our basically the distributed learning paradigm that we talked about before. So generally, when we are leveraging multiple sources of data, when we are leveraging, let's say, multiple sources of computation, we can expect to see significant improvements in performance. Okay, and that's basically one of the motivations that we are using distributed learning in the first place. However, as the name suggests, when you are performing distributed learning, you are doing information sharing, okay? And information sharing typically opens the door to the possibility of sabotaging the security of personal data, okay? So therefore, we want to make sure that we are doing this in a sort of a secure way, such that we are ensuring the integrity of the data, okay? So ensuring the integrity of data or privacy is basically a context here. So therefore, this is an example of what I mentioned, contextually constrained deep learning. All right. So when it comes to data about people, the first thing that may come to mind is the process of anonymization. Okay. So you can basically remove personal identifiers from data and then release that data to the public, or maybe release the outcome of your model that is trained on anonymized data. But unfortunately, this is not going to work due to what we refer to it as the linkage attacks. So essentially, even if you anonymize your data, there exists non-anonymized data out there that the attackers or someone who's doing some malicious activity could link these two such that they could actually de-anonymize the anonymized data, okay? So for instance, let's say that you have some data, so someone's doing some research and they have some data about basically the hospital visits of some patients, okay? Obviously there are some sensitive information here that they want to anonymize, okay? And because they're doing the research, they publish their outcomes and may also publish the anonymized data that they used to conduct the research. However, there is also information out there about the voter registration. Okay, that's public information, that's not anonymized. And there are some features that are shared between these two datasets. For instance, date of birth, gender, zip code, etc. Okay, so what one can do is to basically link these two such that they actually end up de-anonymizing the original highly sensitive data, okay? And a very famous example of this linkage attack is basically the Netflix prize example, where some researchers were able to successfully apply linkage attack to de-anonymize Netflix data by essentially linking that with a publicly available IMDb dataset, okay? So therefore, anonymization by itself is not enough, and we need to resort to other safeguarding mechanisms, okay? In particular, we need to resort to randomized safeguarding mechanisms, okay? And the idea is this, that if someone wants to leverage some data to learn something, they basically need to learn something useful about the population, okay? And they don't necessarily need to memorize or learn something specific about an individual, okay? So therefore, our idea, as we're going to see, is to leverage randomized strategies to make sure that something like this happens. You can still learn useful, let's say, information about the population while ensuring that the model does not memorize, let's say, information about a specific individual, okay? In other words, as we're going to talk about, we're going to make sure that by incorporating randomization, we are reducing the sensitivity of our learning models with respect to individuals. All right. So to see this, let's start with a simple classical example that is referred to as randomized response. Okay. So let's assume that we are conducting a survey to determine the fraction of professors playing a video game. Okay. So this could be considered lame, which in my view is not. So someone who's participating in this survey may not be fully truthful, or they may worry about the response they are providing. Okay. So therefore, as someone who's participating in the survey, or as someone who's conducting the survey, we have to be mindful of this. Okay. And again, what we want to do here, what's our goal? We don't necessarily want to learn whether a specific professor is playing video games or not. We want to learn something useful about the population as a whole. And in this case, we want to learn the fraction of professors playing video games only, okay? And we don't necessarily want to memorize or learn something specific about an individual agent. For instance, it doesn't matter if I play video game or not. The only thing that matters here that we want to find out as while performing this survey is to determine whether like which fraction of the professors play video game. Okay. All right. So let's consider let's formalize this a little bit more, and also consider different ways that people can respond. And we're going to see sort of the trade-off between ensuring privacy and accuracy. And we're going to see how we can leverage randomization to still make sure that we can learn this fraction with a good accuracy while ensuring some level of privacy for people, or in this case, professors participating in the survey. Okay. To that end, let xi denote the truth about whether Professor I is playing game or not. And in this case, x is like a binary variable. 1 means that they are playing video games, 0 means that they don't play video game. Okay, and therefore, because we want to learn the fraction of professors playing video game, let's assume that we have a population of n professors. For instance, in Purdue, we see department n is roughly 120. So our goal is to learn x bar, where x bar is the average of these xi's. Okay. All right. So xi is basically the truth, but when professors participate in the survey, that doesn't necessarily mean that they're going to actually provide this xi to the person conducting the survey. Okay, so let's consider therefore a couple of cases. Let's say that in case 1, they are truthful, meaning that the response they provide, okay, yi, is exactly equal to xi. Okay, so if yi is equal to 1, they are saying that they are playing video game. And if yi is equal to 0, they are saying that they are not playing video game. And in this case, yi is exactly equal to xi. Okay? So therefore, if everyone is truthful, we'll be able to accurately estimate the fraction x bar by just finding the average of the responses that the professors are providing. But the catch here is that we essentially don't have any privacy. Okay? Because everyone is being truthful, the person who is conducting the survey will know exactly which professor is actually playing video game and which one is not playing video game. Okay. So the other extreme case is that we are not providing any useful information whatsoever. Okay. So basically, 50% of the time we're going to be truthful. So the response we are providing is exactly equal to xa. But 50% of the time we are basically lying. Okay, so if you are playing video game, you say that I'm not playing, and if you are not playing, you're saying that I'm playing video game. Okay. So in this case, therefore, the responses that are provided are going to be useless. Okay, and we're not going to be learn or estimate this fraction at all. On the other hand, we're going to win on the privacy front. Okay, so basically, the reason is that the responses that the professors are giving us, yi's, are completely independent of the truth. Okay, so if someone look at the responses, they don't know anything about the truth basically. Okay, but the catch is that we are not learning anything useful about the population either. Okay, okay. So these are the basically two cases, two extreme cases. In one case, we are completely truthful. In another case, we basically are responding randomly. Okay, so don't provide any information. So a natural, therefore, thing that comes to mind is to interpolate these two cases. Okay, and this is indeed what we want to do. Okay, so let's interpolate these two cases. Basically, let's say that you're going to respond truthfully, xi, with probability half plus some epsilon, and you're going to basically sort of lie, so 1 minus xi, with probability half minus epsilon, where epsilon here is basically some parameter which is between 0 and half. Okay, so therefore, if epsilon is equal to half, what this means that we get case 1 back. We're going to be truthful all the time. On the other hand, when epsilon is equal to basically 0, it means that we are just responding randomly. So we're going to recover case 2. So we're going to basically make sure that epsilon is sort of strictly larger than 0 and let's say strictly less than half, such that we interpolate these two cases. And when we enforce that epsilon is strictly larger than 0, in particular, basically what is going on here is that on average it is more likely for the responses to be truthful than not. Okay. So therefore, in some sense, we are providing plausible deniability, and intuitively, given that we are in some sense providing some information, there is some correlation between the responses that the professor is giving us and the actual truth. We should be able to learn the fraction, so the quantity of interest, with certain accuracy. Okay. All right. So let's see how we can do this. So first of all, we're going to look at the mean of these yi's. Okay, because yi is a random variable, and another reason that we are looking at the mean is to basically see what kind of estimator of the fraction we can form. Okay, and in particular, what is the performance of that estimator. Okay, and again, using the language of estimation theory, performance typically is captured by, let's say, mean and variance. Okay, so we want to basically calculate basically the mean and the variance of the estimator of the fraction. Okay, so let's look at the mean of the response. Again, we are providing the truth with probability half plus epsilon, and we are lying with probability half minus epsilon. Okay, so that's the mean of y. So you can simplify it to get this expression. What this is saying is that this is not equal to xi. The only case that is equal to xi is when epsilon is equal to half, which means that you are always truthful, and that does make sense. Otherwise, there is some bias. Okay, so the intuitive idea of therefore averaging these yi's is not going to be a good estimator of the true fraction. Okay, but given this simple form, what we can do some rearranging to actually get an unbiased estimator of xi, and therefore take the average of those. Okay, in particular, after receiving the answers, if the person who is conducting the survey knows these epsilons, they can form this new estimator y hat. Okay, and this is actually very simple to see that is going to be an unbiased estimator of xi. Okay, so therefore for each response they're going to form this y hat, and then they're going to take an average over the entire population, over the entire pool of professors, and then this will be a good estimator of the true fraction x bar. In particular, it will be an unbiased estimator, and under some assumptions, for instance, assuming that the responses are statistically independent, and using some basic techniques, you can sort of bound the estimation error. Okay, so in some sense, this is the variance. So what is this saying is that when epsilon is equal to half, meaning everyone is truthful, we get perfect estimation. If epsilon is equal to 0, when everyone is lying, we can't basically we can't get any useful bound on the estimation error. So these correspond to those cases we talked about before. Okay, but when epsilon is between 0 and 0.5, we can still get a meaningful bound on the estimation error, and in fact, the bound goes to 0 as we include more and more professors in our survey. Okay, so in particular, as n goes to infinity, we get an excellent estimator of the true fraction. Okay, so this is basically doing exactly what we intended. We are learning something useful, in this case the true fraction, with a very good accuracy about the population, and we are not memorizing or learning something specific about xi's, because the responses that are provided by professors are sort of perturbed with noise to make sure they are maintaining some degree of plausible deniability and therefore some degree of privacy. So this is basically a simple example of showing the power of including noise to maintain privacy. And in the next video, we're going to sort of formalize this into a powerful formalism which is referred to as differential privacy. I'll see you there.